Hi there, welcome in this new video in the Optimisation channel. This time we'll look at the exam of June 2025. As usual, what we'll look at is the exercise questions for the theory. Well, you have to have a look at the theoretical course. Well, let us first start with questions 1 and 4. In the first question, you have to find all the local extrema and saddle points of the function that is given. And in question 4, you have to apply the Newton descent method to this same function and perform the first iteration with step size 1, starting from the initial point x0, y0. If you're preparing your exam, it's time to push the pause button. Well, let us have a look at the solution of this first question, which involves taking partial derivatives with respect to x and y. Let us take the partial derivative of the function with respect to x. What you have to see here is that you have the product of two functions. This is the first function here that depends on x, and the second function that depends on x. And therefore, when you take the derivative, you take the first function, here it is, and then you take the derivative of the second function with respect to x, and this is a -1. Then you take this function over here, you write it, and you take the partial derivative of the other one with respect to x. This is 3 minus y. This it can be seen as a constant with respect to x, and then you take the partial derivative with respect to x, and that's a 1. If you rewrite this, this is what you obtain. And you can do something similar for the other partial derivatives and also for the second derivatives, and this is how you obtain the gradient and the Hessian. For the critical points, you remember that you have to set the gradient to 0, and if you look closely, you will see that there are 4 solutions. These two here over here make these ones 0, right? This one over here make these two 0, and if you take 2, 2, you will also make these two here 0. So you have 4 critical points, and based on information on the Hessian, well, you have to decide what they are, local extrema or saddle points. If you plug in 3, 0 in the Hessian, you obtain something like this. If you compute the determinant, you see it's negative, right? So lambda 1 and lambda 2, the two eigenvalues, will have opposite sides, so the Hessian is indefinite, so we have a saddle point. For the two next critical points, you will have something similar. You can see here that the determinant will be negative, and here as well. So for these two critical points, we know that they are saddle points. And then we're left with the last critical point. If you plug in, you obtain this Hessian over here, and here the situation is different. The determinant is positive. You can see that the trace is negative, so the two eigenvalues are both negative. So H is negative definite. We have a local maximum. Why is it local? Well, you can show that this function here is unbounded. The easiest way to see this is to set x is equal to y. Then this function becomes this thing here over here, and you can see that you can make it as high or as close to infinity if x goes to infinity. So this function is unbounded, so this must be a local maximum. So as usual, we should check this in MATLAB. So what I've done here is, well, make a surface plot of the function that we have considered, and what you see over here are the 4 critical points. Well, the 3 first ones are the ones that are corresponding to a saddle point, and they will be marked with a red dot, and the local maximum will be noted with a magenta point, right? So if we do this, this is what we obtain, and you can clearly see indeed that the 3 critical points in red are the saddle points, and that we have a local maximum in 2, 2. So this seems to be correct. Let us now have a look at question 4, and for that we can reuse what we have done for question 1, right? For the descent direction, since we're using Newton's descent method, we need the gradient evaluated at, well, the initial point, and the Hessian evaluated at the initial point, right? So if you plug in x is equal to 1 and y is equal to 2 in these expressions, this is what you obtain for the gradient, and this is the Hessian, and these two are both evaluated at the initial point. For the descent direction, we need to take minus the inverse of the Hessian evaluated in x0, y0 times the gradient evaluated at this same point. So we need the inverse of the Hessian in x0, y0. This involves taking the determinant, so you have, it's minus 1 over here, 1 over the determinant, right? You switch these two and you change these two in sign. This is what you have over here, and you can rewrite this as follows, right? I haven't done it, but you should do this at the time of the exam. If you multiply this one with this one, you should of course have an identity matrix. Then you can compute the descent direction, right? Minus the inverse of the Hessian, here it is, times the gradient. If you do the computation, this is here the descent direction. And here is your first iterate. You start from the initial point and you do a step of size 1, alpha is equal to 1, in the descent direction. If you do the computation, this is what you obtain as a first iterate. And this concludes question 4. You can check this if you want using the software that is also available on the web page of the course. So we use one iteration since we only want one iterate. Here is the step size, here's the function, here's the initial point we start from, and we use Newton's descent direction. If we run this code, you can immediately see that we start from exactly 1, 2, and we go to minus 4, 1, which is in line with what we have seen. You can also see here the intermediate steps, which are also correct. Here the x, as I said, minus 1, 4. So this seems to be correct. Well, let us now have a look at question 5. In this question, you have to solve a linear programming problem using the two-phase simplex method. If you're preparing your exam, it's time to push the pause button. Well, let us have a look at this 5th question. We start with this minimization problem, but we have to bring it in the standard problem, in the standard format. In a standard problem, we have a minimization problem, so this we can keep, but we have to transform these inequalities in equalities. For the first and the third equation, we have on the right side positive numbers, right, and we have smaller or equal, so we can transform this into an equality by using slack variables that are positive, x4 and x6. Here we have an inequality, but on the right side a negative number, so we have to change this. So the easiest thing to do is to multiply this equation by minus 1, and this is what you obtain. Of course, you'll have a change in the inequality from smaller or equal to larger or equal. Here we have now on the right something positive, and we can transform this one here in an equality, but now we have to use a surplus variable x5, which is constrained to be positive. This is our standard problem we have to start from. Here, it's not obvious to find a basic feasible solution to start with. This is because of this minus over here. So we'll start with stage 1, which is an artificial problem, and well, the idea of this artificial problem is to find a basic feasible solution, right? And in order to easily find a basic feasible solution to start from, well, you have to add this artificial variable x7 that you're going to minimize, right? At the end of this stage 1, you should obtain x7 is equal to 0, and the variable will disappear from the problem, and you'll have your basic feasible solution to start from in stage 2. So if we put this in a tableau form, this is what you obtain. You take your cost and you write it below, right? This is the row that you see here that has been crossed. But why is it crossed? Well, you have to look at the pivots. They are in columns x4, x6 and x7, and you know that what you should have is zeros above the pivot and below the pivot. So this is okay for column x4, x6, but not okay for column x7 because we have this 1 here. So before we start with anything, we have to make a 0 below this pivot in x7, and this is simply done by this elementary row operation. If you perform it, well, this is what you obtain. And now you're ready to start with the artificial problem. So maybe if you have stopped here, it's time to push the pause button and to try to continue by yourself. Well, let us continue. Before we continue, I had made a small mistake over here. I had a 2 over here, and obviously it had to be a 3. So there was a slight mistake up to now. It's corrected over here. So if we look at the tableau that we have here, we see here that there is only one reduced cost that is negative. So we know the variable that is going to enter the base, which is going to be x2, as you see over here. We need to decide which variable is going to leave the base. For that, we compute this thing over here, which is really the column B, and then you divide by the corresponding element in column x2. 5 divided by 1, 5, 1 by 1, 1, 5 by 2 over here, it should be 5 over 2, right? So the smallest one that is positive is clearly this one over here. So we know that the variable that is going to leave the base is x7. So we know that the next tableau will be at the end of stage 1. This is our new pivot. In order to create zeros above and below the pivots, we need to perform these 3 row operations. If you perform these row operations, this is the final tableau of stage 1 that you obtain. As announced, the basic variables are x2, x4, x6. So here you have the pivot, and you see here clearly that x7 is equal to 0. We have now a basic feasible solution that we can start from, and it is x2 is equal to 1, x5 is equal to 4, and x6 is equal to 3. So now we can cross out this column, cross out this cost, and replace it by our cost over here and start stage 2. Well, if you're preparing your exam and you have arrived up to here, maybe it's time to push the pause button and to try to continue by yourself. So we can now start stage 2. For that, we copy the tableau. By the way, the pivot was at the wrong place over here. The pivot is of course in the column that corresponds to the basic variable. You skip this column, this row over here, and you have to write the cost that you see over here, right? So we have the basic variables, the pivots, and of course before we start we have to make sure, as usual, that there are zeros above and below the pivot, which is clearly not the case over here because we have this -3. So before we start, we have to perform this row operation in order to create a 0. If you perform this row operation, this is what you obtain. And now we are ready to start stage 2. If you're preparing your exam, well, try to do this by yourself and push the pause button. In the previous tableau that we had obtained, the reduced cost that is the most negative one is this one over here. So we know that x3 will enter the base. We need to decide which variable is going to leave, and this is why we compute this column over here. So it's the column B here divided by the corresponding elements of column x3. So 4 divided by 2, 2. Here this one is negative, so we leave it out. And 3 divided by 3 is 1. So the smallest one that is positive is clearly this one. So this means that x3 is leaving the base and x6 will leave the base, as you can see over here. This will be our new pivot when we have to perform the following row operation to create zeros above and below, and to make the pivot 1 we have to multiply not by 2/3 but by 1/3. This way it's correct. So if you perform these row operations, this is the final tableau that you obtain. You can see that it's the final tableau because the reduced costs are all positive. So you can read the solution first in terms of the initial variables. x1 is not a basic variable, so it's 0. x2 is a basic variable, it's 4. x3 is a basic variable and it's 1. And here we have the slack and surplus variables. x4 is equal to 2 and the other ones are equal to 0. You can read the cost over here. You'd have to put a minus sign in front. And then of course you can check, right? You take your cost over here, you plug in the solutions and you see that indeed it's equal to minus 10. You can also look at these equations here and you can see that they are met. Here you see that x4 is equal to 2, so we have a slack of 2. So here in the first equation we'll have an inequality, right? Whereas we have a surplus of 0 and a slack of 0 in equation 2 and 3. So this means that these two equations here are met with equality. So this concludes exercise 5 of the exam. And question 6 concludes this exam. You have to use the Lagrange multiplier method to optimize a function subject to a constraint. As usual, if you're preparing your exam, try to do this by yourself and push the pause button. So this is a Lagrange type problem with the function to minimize f. We can also write the constraint. So if you take the 24 on the other side, we have that this quantity has to be 0. This allows us to write the Lagrangian, so it's the original function f plus the Lagrange multiplier times the constraint, right? We have transformed a constraint optimization problem in an unconstrained optimization problem with an additional parameter lambda. As usual, what we do is compute the partial derivatives with respect to all parameters, so x, y, z, and lambda, and we obtain these 4 equations, right? These are equations that are nonlinear, so you have to find a solution to obtain the final solution here, so you have to be a bit creative. What you can do over here is multiply the first equation by x, the second by y, and the third by z, because you'll have the same quantity appearing, right? And if you do this and you keep this quantity to the left, you see that you have this equal to this is equal to this, so we can say that this quantity is equal to this quantity is equal to this quantity. This is what written over here. You can simplify this equation here by minus 2 lambda, and this is what you obtain, right? So now you can inject this in this equation over here. You can see that this is y, this is z over here. Z is, well, it's not y, but this is y square and z square. This is correct. So we have 6 times x squared is 24, so x squared is 4, so we have x is equal to plus minus 2. Y squared is 8, z squared is 8, and so we have y and z equal to plus minus 2 times square root of 2. So there are 8 combinations. The 8 combinations are written over here. To know if it's a minimum or a maximum, well, you have to plug in here, right? And you can see that if for instance, the product of the 3, because this is what is appearing over here, is positive, it's of course a maximum. Over here, the product of the 3 is negative, so it's a minimum, right? And therefore you can classify them as follows, as maxima or minima. And this concludes question 6 and also this exam of June 2025. Thank you for watching.